All right, ladies and gentlemen, welcome to today's trigonometry class. And today, the topic that we're going to see in today's class is um excuse me for a second. The topic that we're going to see in today's class is trigonometric functions in the Cartesian plane. Now, before we get into the examples, which are really not that complicated, let's go a little bit over a little bit of some of the theory. So we know from chapter 1 when we work with right angle trigonometry that there were six basic trigonometric functions: sine, cosine, tangent, cosecant, secant, and cotangent. And we defined them in chapter 1 as um, z is greater than 0, but z is less than 90 because we were working with the right triangles. So here we're actually looking at working with the same six basic trigonometric functions. However, we're working from a Cartesian plane. And for those of you that don't remember, Cartesian plane is basically our x and y axis, at x and with the x and y coordinates that are down here. So this is a Cartesian plane, what I drew down here in black. Okay. Now, the definition is going to vary a little bit in this section and in this chapter because now we're working with trigonometric functions, the same six, but on a Cartesian plane. So the first thing that we have to understand is that the hypotenuse, which in chapter 1 we calculated using the Pythagorean theorem, is now going to be calculated by using the distance formula, which is kind of a derivative of the Pythagorean theorem. And instead of saying c, we're going to assume that the distance is r. So this definition says that the distance r from the origin 0, 0 to the point xy can be found by using the distance formula. It says since r is a distance, it is always positive. So in this case, our hypotenuse, our r, is always going to be positive because we're starting from the origin. So if we look at this triangle that I drew down here, r, notice that is basically the hypotenuse, and it's going to be positive because technically it's if we're looking at it in this side, it's in quadrant 1, and that would be positive. So r is going to be greater than 0. And basically, if we had the origin 0, 0, we would say, well, that r is actually the square root of x squared plus y squared. So our answer is always going to be positive in this case. All right. Now, the definition of finding trigonometric function values in a Cartesian plane is basically this one. It says, let x, y be any point other than the origin on the terminal side of the standard position. Let r be the distance from x, y to the origin. Then the six basic trigonometric functions can be defined as the sine of z is y over r, the cosine of z is x over r, the tangent of z is y over x, the cosecant of z is r over y, the secant of z is r over x, and the cotangent of z is x over y. So cosecant is r over y, secant is r over x, and cotangent is x over y. Mind you, especially when we're working with fractions, that the denominator cannot be 0. Now, basically what that definition means is that the r, which is going to be our hypotenuse, is going to be calculated using the formula r equals x squared plus y squared, where x is going to be the or any number here in the horizontal, and y is going to be any number on the vertical side. It's not to say that x and y can't be negative. It's just that r is going to be greater than 0, okay, because it's a distance. So now let's look a little bit at the example that is in your textbook. And this is we're going to do example 1 and 2 real quick. And they may seem extremely different, but the reality is that they're quite simple to use. And actually, let's leave this. Let's leave this. What I am going to erase is actually this right here. and this right here so we can have some space. Now the problem in example 1 says the terminal side of an angle or angle Z, the terminal side of angle Z, I just didn't have the opportunity, so let me write it here. The terminal side in angle Z, the terminal side of angle Z in standard position passes through the point 2 and 5. Calculate the value of all 6 trigonometric functions. So 2 and 5. So that means that x is going to be 2. One, 2, and y is going to be 5. So 1, 2, 3, 4, and 5. And what we would do in that case, 1 second, ladies and gentlemen. Here we go. Is we would say x equals 2 right here. Let me change the x equals 2. And y equals 5. And now we're going to find r. Give me 1 second, ladies and gentlemen. I'm confronting some technical difficulties here. So give me 1 second, and I apologize for the inconvenience, but hopefully now we will get rolling real quick. Awesome. And okay, x equals 2, y equals 5. And the ordered pair is right here. So the first thing we're going to do is, in order to find all 6 trigonometric functions, I know I have a ordered pair of 2, 5, which means that x is 2 and y is 5. So I'm going to use these numbers to actually find r. So I'm going to say r equals, in this case, the square root of let me move this so you guys can see what I'm doing. The square root of x, which is 2 squared, plus 5, which is y squared. And that would be the square root of 4 plus 5. Give me 1 second, guys. Let me... Okay, 2 squared. Let me fix that. Plus 5 squared. And that would be the square root of 2 squared is 4. So that would be 4. And 5 squared is 25. So that would be the square root of 4 plus 5. 4 plus 25, excuse me. Which of course is the square root of 29. So that means that the distance is actually the square root of 29. Now we don't need a calculator. We don't need the exact value. We're going to leave it expressed. So I know that this is the square root of 29. And now with this information, I can find the 6 basic trigonometric functions. Of course, remember to rationalize your square root. So again, this is the square root of 29. And that was pretty bad. Let's see if I can just square root of 29. No, that does not look good. 29. That one is better. So r is a square root of 29. So what I'm going to do now is find the sine. So if I'm going to find the sine of that, remember that here is where my angle is. So let me shade that in a different color so you guys. So z is here because according to the definition, no, let me use a different color. The angle z is here. Angle z is here. Right from where the hypotenuse goes, this is where angle z is. So basically, if I want to find y over r, or the sine in that case, sine is opposite over hypotenuse. So the farthest, now let me make some space here. Okay, so sine, if this is where z is, because this is where r is, 5 over the square root of 29, because 5 is my opposite and the square root of 29 is my hypotenuse. And then later we're going to rationalize those denominators. Okay? And of course, the cosine would be 2 over the square root of 29, because 2 is the closest angle to z. So that would be 2 over the square root of 29. And the tangent would be the opposite over the adjacent. So, of course, that would be 5 over 2. And we have our first three, trigonometric functions. And now we're going to find our other three. So the cosecant is the opposite of the sine. So the cosecant would be the square root of 29 over 5. Likewise, the secant would be the square root of 29 over 2. And the cotangent would be 2 over 5. So I have my 6 trigonometric function. The only thing I need to do is just rationalize the sine and cosine, because the other step is just to rationalize the denominators. And if I notice, both the cosine of 29, or both the sine and the cosine have the square root of 29 as my rational. So let's go ahead and do that real quick. See if I can do it here. So sine is 5 over the square root of 29. And remember that whenever you're rationalizing a denominator, all you're going to do is multiply both sides by that. So this would be times the square root of 29. Times the square root of 29. And these two cancel out in the denominator, and that would be 29. And 5 times the square root of 29 would be my numerator over 29, which is my denominator. And that would be the sine of z in that case. Now I'm going to do the same thing with the cosine. And the cosine actually has 2 over the square root of 29. So 2 over the square root of 29, I do the same thing. And I basically just multiply by the square root of 29. Now remember, in the denominators, not that they're miraculously canceling out. It's just that you're multiplying the square root of 29 times the square root of 29. That's going to give you the square root of a large number. And when you find the square root of that, it gives you 29. So again, specifically here, it's not that they're going to miraculously cancel out, ladies and gentlemen. It's just that you're going to multiply them. And they're going to give you a number with a perfect square root. So if you multiply 29 times 29, that's going to be the square root of 841. And the square root of 841 gives you 29. It's just that I'm skipping that step. And I'm writing my answer as 29. And of course, since I don't know the value of 29, I leave my answer expressed as 2 times the square root of 29. And that's pretty much how you do example number 1. Example number 2 is very similar to example number 1. Example 2 basically has the same situation, but it's non-acute angle. So let me go ahead and clear these drawings. And let's write example number 2. Now, before we go to example number 2, it says we can now use the second definition of trigonometric functions to find the value of any acute or non-acute angle as well. It says, note, in example number 1, we could have used the values of sine, cosine, and tangent functions along with the reciprocal identities to evaluate the cosecant and secant. Example number 2. Example number 2 says the terminal side of an angle Z one second, ladies and gentlemen. The terminal side of an angle Z in standard position passes through the point -4, -7. Find the 6 basic trigonometric functions. Okay, so we're going to draw the figure, and we have our Cartesian plane. And we have our ordered pair -4. So that means that x is going to be -4. 1, 2, 3, and negative 4. And y is actually going to be negative 7. And we have 4, 5, 6, and 7. Okay, so let's just kind of figure out or draw that triangle right there. And we have negative 4. And down here we have negative 7. So we have negative 7 is actually here. So let me erase this because I made a mistake there. Now, negative 4, negative 7, x is negative 4. This is like that line that's not really there. And since this is negative, that means, or since this is in standard form, that means that this is where I'm going to find the distance or the hypotenuse. Which means that this is where z is going to be. Because remember that we're assuming that the angle is in standard position. So this is where z is going to be, right here. And we're going to use the formulas to calculate the value, the distance. So we're going to say r equals, in this case, the square root of negative 4 squared plus 7 squared, or negative 7 squared. And this is going to be the square root of 16 plus 49 and that's going to be the square root of 65. So I know r is actually right here, and it is actually the square root of 65. Now I did that on purpose so that it doesn't look it doesn't kind of get lost there, but just not that it has to be that big or has to be written specifically there. Now that I have the information, I can find the basic trigonometric function. Now remember, the angle in this case is going to be here because this is where we assuming that the angle of standard position starts. Okay, so we're going to find the sine, the cosine, and the other 6 trigonometric functions. Now to find the sine, we know it's opposite over hypotenuse, or y, right? Or opposite over hypotenuse, excuse me. was going to say something, but I don't want to get ahead of myself. So in this case, the farthest angle from Z would be my opposite, and the closest, and the hypotenuse is the square root of 65. So 7, which is down here, this is a 7. Let's see if I can write it in, let's see if I write it in blue, and it looks a little better. No, it doesn't. So this is what I'm going to do. Let me change the color of the -7 right here. And that way you guys can distinguish it a little better. So this down here is the -7. So this is -7, and this is Z, which means that it would be -7 over the square root of 65 the cosine of Z, of course, is in this case -4 over the square root of 65. The tangent would be -7 over 4, because it's opposite over adjacent. And now we do the cosecant, which is pretty much the opposite of the sine. So that would be the square root of 65 over -7. The secant, which is the opposite of the cosine, is the square root of 65 over -4. And the cotangent, which would be for, this is -7, I'm sorry. The cotangent, which would be -4 over -7. And in your book, they'll even cancel out the negative signs and write it as a positive fraction, which is fine. Notice, let me highlight that point for you guys. Notice how here it's -7 over -4. So sometimes you'll see it as 7 over 4, and you'll see it as, in this case, 4 over 7. It really is the same thing. So, don't worry. I mean, if you leave the negative signs expressed or not, eventually they are going to cancel out. So if you leave them expressed or don't leave them expressed, that's fine. I just want you guys to understand, right? Uh, just in case you see something different. Now, the last step is to rationalize denominators. So let's go ahead and rationalize denominators. And of course, we have the cosine and the sine functions, which whose denominators do need to be rationalized. So let's see if I can erase this without erasing the story problem. Apparently not. Okay. The struggle is real, ladies and gentlemen. Now let's rationalize these denominators. So the sine of Z is -7 over the square root of 65. And you're simply going to multiply by the square root of 65. And of course, like I said, it's not that they miraculously cancel out, but if you multiply the square root of 65 by the square root of 65, you're going to get a number whose square root is 65. So basically that's it. And because I don't know what the exact value of the square root of 65 is, I leave my numerator expressed as -7 times the square root of 65. And pretty much I'm going to do the same thing for the cosine of z. And basically the cosine of z is going to be um, -4 over the square root of 65. And the same thing, guys, the process is very repetitive, and you don't have to necessarily do this process at the end. If you're looking for the 6 trigonometric functions and you want to do that right away, you can. There's no, like, it doesn't have to be this way. I'm just doing it because it's easier for me to get the the functions and then just work with this, but really makes no difference. And then again, you multiply by the square root of 65. Remember, the denominators are going to equal a number that is a large number whose square root is actually 65, and that's why the denominator is now 65. And again, because I don't know what the square root of 65, the exact value of the square root of 65, I leave my numerator expressed as -4 times the square root of 65. So guys, these are the first two examples of this new section, calculating trigonometric functions for acute and non-acute angles. So hopefully this video will be of great help to you guys. If you have any questions, you know where to find me. So stay safe, and we'll see each other in our next class. So bye-bye.